Hello. I want to explain how to solve uh, another system of ordinary differential equations, such as the ones written here. Um, Now, the reason why I want to do another video on this system of two differential equations, is because I have done videos before. I've noticed in one of them, although I got the correct answer at the end, I did make some glaring errors, um, and rather than deleting that video or correcting it, I thought, well, I'll leave that for you to have a look at, and hopefully the errors will keep you on your toes and you'll see where I went wrong, and perhaps learn just as much about how to solve such a system. Um, so the system here that I want to solve for you today um, are from the book called Differential Equations. They're in chapter 4 on page 180. The book is by Dennis G. Zill and Michael R. Cullen. So basically, what we're going to do to solve these two equations is to use matrix methods, as I used in my previous video some time ago. Um, so hopefully I'll be able to back up those videos and the information in them by now returning to this system, which we're going to solve in the same sort of way, using identical methods as before. So we've got two equations here. X dot means dx by dt, but we just write it for brevity as x dot, and that's equal to 2x plus y plus t minus 2. This equates the next equation that is paired with this equation above it is y dot equal to 3x plus 4y minus 4t. So this is a coupled system of equations, which is what I was trying to say before. So let's refer to this equation as being equation 1. I'll just change to the black ink. So that's equation 1, that's equation 2, and these two equations are coupled. So what we can do is, to start solving this system of equations, we can write them in matrix form. So we've got x dot and y dot, and that is equal to the matrix. Well, the first entry is 2, the next entry is 1, the entry down here is 3, that's in the next coupled equation, and in the next coupled equation, the second entry there is 4. And we effectively take out the x's and the y's and write them in this column vector here, because when you multiply this matrix out again, you get 2 times x plus 1 times y, and let me just change color to explain what you do for the next. So you get 2 times x, which will give you the 2x there, the 1 times y, which will give you the y there, and for this next coupled equation, the second one, equation 2, you would have 3 times x to give you the 3x, and then you would have 4 times y to give you the 4y there. So we'll just get rid of those coloured lines now, and proceed with writing down the rest of the matrix. So what we have here is a plus t in the first coupled equation, that is. So we'll put a plus there, and we'll write down the coefficient of t is 1. So we'll write a 1 there, and in this second coupled equation, the coefficient of t is -4. So we'll write a -4 there, and all we need to do is write the t outside the vector. And of course, we add on the constants, which are in the first entry, we've got -2. That's the constant in the first coupled equation. And in the second equation, we've basically got +0. So we can write, I'll just delete that and then we don't spoil the equation. So we've got a 0 there. And we'll call this system 3 or equation 3. Let me just write that in. 3. Right, okay. So now that we've got it in matrix form, we can start to solve this system. And what we bear in mind is that, let me just change that to red. This matrix here is A. So A, perhaps we should write in black ink for that. So we've got A equals 2, 1, and 3, and 4. Right, now solve this equation. We need to find the determinant of A. So need to find the det or determinant of A, and we find that when the determinant of A is equal to 0. So the determinant of A is equal to the determinant lambda I minus A. Now I always write it round that way, with the lambda I first and then the actual matrix A subtracted from it. Many mathematicians, in fact most mathematicians, would write this as, and I'll just write it in the margin here, would write that as A minus lambda I. But I am very, very dyslexic, and writing it round this way causes me problems involving minus signs, and I make extremely glaring errors. So I prefer to write it round this way, which is absolutely fine because the determinant is always equal to 0. So in this particular case, the determinant A minus lambda I is equal to 0 is exactly the same as multiplying both sides by -1 to get minus A plus lambda I. I don't think I can quite get that on, or if you like, excuse me, making a bit of a mistake there. So that can be written as lambda I minus a equal to 0. Okay, so we find the determinant lambda I minus a, and so a becomes, and I'm going to write this in green. So the determinant of a becomes, there we are, determinant of a becomes the following: lambda minus 2 minus 1 there, and minus 3 here, and lambda minus 4, and that's equal to 0. Now then, how do we find the determinant of a from this this setup here? Well, we multiply the lambda minus 2 by lambda minus 4. So we've got lambda minus 2 times lambda minus 4. Make that look more like a lambda. Minus a minus 1 times a minus 3. And that is equal to 0. Mustn't forget that. Now, when we multiply this out, we get lambda squared minus 2 lambda minus 4 lambda plus 8 minus 3. And this simplifies to give lambda squared minus 6 lambda plus 5 equals 0, and that's equal to 0 up there as well. So we can factorize this quadratic equation in lambda, which is the easiest thing to do rather than using the quadratic formula. And so we get lambda minus 1 times lambda minus 5 equal to 0. So you can see that lambda times lambda is lambda squared. Lambda times minus 5 minus lambda times minus 1 gives you the minus 6 lambda. And then you've got minus 1 times minus 5, which gives you 5. So this is the correct factorization of this quadratic. This means that either lambda minus 1 is 0 and or lambda minus 5 equals 0, leading us to the eigenvalues of lambda equals 1 and lambda equals 5. Right? So we've got two eigenvalues. Now the next step is to find the eigenvectors. I hope I called those the eigenvalues. Yes. So those are the eigenvalues. Now we have to find the eigenvectors. So we have our matrix. Well, we'll just write it like this for now. We have lambda minus 2, minus 1, minus 3, and lambda minus 4. That was the det anyway. So the det of A was equal to that. But if we just take what we have on the right hand side and rewrite this as the matrix lambda minus 2, minus 1, minus 3, and lambda minus 4 multiplied by the column vector x and y, because it is a matrix, then we can substitute in our first value of lambda. So we substitute in lambda equals 1. We'll use that one first, and next we'll use lambda equals 5, but first this one. So what we have is 1 minus 2 minus 1 minus 3 and 1 minus 4. And that's all multiplied by x and y. And by the way, I have forgotten to write something down, and that is equals 0 on both sides. You could just write 0 like that, but I'm going to put 2 zeros in. So it's just a 0 vector. So if we simplify this matrix, we've got 1 minus 2, which is minus 1, and we've got minus 1 here, we've got minus 3 here, and we've got minus 3 here. And that they are all multiplied by x, well, the column vector x, y, and that's equal to 0 and 0. Right? Now, what you might see from, I'll just highlight this in here, what you might see from each equation effectively, because that's what they are in this matrix, we have, we multiply the minus 1 by x and this minus 1 by y, we get minus x minus y equals 0, and the minus 3 times x is minus 3x minus 3y equal to 0, and this is exactly the same as x plus y equals 0, and this is exactly the same as, well, you can cancel both sides by 3 on this one, so you get x plus y again. So you're cancelling both sides of the first equation there by minus 1 to get x plus y equals 0, and here you cancel both sides by minus 3 to get x plus y again. So both of those equations are consistent with each other. So what we do is we just take one of them and consider, well, let me write in a different colour. Let's write in black. So consider only x plus y equals 0. Now, what values of x and what values of y do we need to make the left-hand side equal to 0? Well, actually, you've got an infinite number of values for x and y to make the left-hand side equal to 0. But we'll choose the simplest ones. And I'm going to choose x equal to minus 1 and y equal to 1. Because as you can see, we've got, if we substitute minus 1 and 1 back in for x and y respectively, then we get, we'll just check that, we get minus 1 plus 1 equals 0, and we verified that. Okay, so we've got an eigenvector, and the eigenvector associated with lambda equals 1 is, and we'll just scroll up a little bit, we'll call this V1 equal to, I'm not going to put any constants in yet, is equal to -1 and 1, right? So now we've done that first part, and we go back to the matrix, lambda -2, -1, -3, lambda -4 multiplied by x and y, okay, and that's equal to 0. Now, for lambda equals 5, we have, I think it was 5, wasn't it? Yep. We have 5 -2, -1, -3, and 5 -4. And that's multiplied by x, y, the vector x, y, and that's equal to 0 and 0. Okie doke. Now, what does that matrix come out to be? Well, 5 -2 is 3. The -1 stays as it is. The -3 stays as it is. And we've got 5 -4, which is 1. So you can see the minus signs are reversed and the plus signs are reversed here. But that is not a problem. That's what we want, ideally. So let's just write the 0 vector there. Now, both of these equations imply, well, we can just write the first equation out. So we'll write that in green. So we've got 3 times x is 3x, minus 1 times y, which is -1y, equal to 0. And then we've got -3 times x, which is -3x, plus 1 times y, equals 0. Now these are exactly the same as, well, I'll just run through it again and then hopefully you've got it. That stays the same, but you divide both sides of this second equation by -1 to get 3x minus 1y equals 0. So you can see both equations are identical and consistent. So what values of x can we have? So let me just write this down. For 3x minus 1y to equal 0, we can choose x to be equal to 1 and y to be equal to 3, because if we substitute 1 in for x, we've got 3 times 1 minus 1 times 3. And what's that equal to? Well, that's 3 minus 3 equals 0. Right, so we've got thus an eigenvector associated. So it's like the direction, directional vector. That's an E vector associated with lambda equals 5 is V2, we'll call it, equal to, what did I say? Let's move this down a little bit. Equal to 1 and 3. That's not a very, it's a little bit cramped. Let's just make that a bit bigger. So 1 and 3. So actually, a complementary function, if I've got that right, is the complementary function is x and y is equal to, in fact, actually, we want a constant in there, a times, and if you remember, our first eigenvector was -1 and 1 associated with the eigenvalue 1t, but of course we don't write 1t, whoops, we only write t there, plus b times the eigenvector, which is this one here, 1, 3, associated with the eigenvalue 5. So we write down 5t there. Now, we're not finished because we now need to consider the rest of the matrix that we wrote down. Now, I'll just write it down again here, just for your benefit. So we've got x dot, y dot equal to 2, 1, 3, 4, and that's multiplied by the vector x, y, x and y, plus 1 minus 4, t, plus -2 and 0. Right, okay. So we now need to try for a particular function and work out what the particular function is. Well, as you can see from, we'll just change to a red colour. Let's get some red there. Right, this part here is of the form a t. If you multiply the 1 by the t, you get 1t there. -4 times t is just -4t. But of course, that is of the form, so this entry here, 1t, is of the form at, and underneath in the matrix, we've got -4t, which corresponds to bt. In fact, actually, we'll call that ct. Doesn't matter what you call these things. It's just convenient for the following reason. And in that matrix, we're going to add on another constant corresponding to the -2. So we'll add on b, right? So the -2, or rather the b, corresponds to the plus -2. And of course, down here, we've only got 0, but we still have to write an unknown constant down in place of that, or corresponding to that anyway. So we'll call that d. Okie doke. Now, that is what we let x and y be equal to. So it's a bit like doing a single ordinary differential equation, which what do we call those equations? I've forgotten the name of them now, but something like x double dot minus 3x dot plus x is equal to e to the power t. So you choose a particular function of a e to the t, or you try that, and if that didn't work, you try a t e to the t. I can't remember the name of. I think they're non-homogeneous equations or something like that. But you get the drift. So that's the sort of thing we're doing here. Now we'll consider this here. So if we just return to black ink, then we'll rewrite this down. So we've got x and y, and that's equal to a t plus b, c t plus d. Now, what we want to do is differentiate that, because we need to substitute the derivative of both sides of this. Well, we need to find the derivative of the left-hand side and the right-hand side, because once we've found x dot and y dot, we substitute the derivative of this, which we'll find in a moment, back into the left-hand side of this equation, along with this matrix here back into the vector x, y there, and then solve a system of simple equations to find a, b, c, and d. So this differentiates this matrix here. This becomes a and c, just that. So AT differentiates to give A, B disappears, CT differentiates to give C, and D disappears. So I can't remember how many equations we labelled. I think we only labelled, we've got equation 3 there. So let's just go down to there. So this was equation 3. So I'm not relabeling it, but that means that this is equation 4 and this is equation 5. So I'll write this down for you. Substituting equations 4 and 5 into equation 3, we get so we get a c there. That's the derivative of our homogeneous complementary function, and that's equal to 2, 1, 3, 4 multiplied by a t plus b and c t plus d, plus the other bit, which is t and 4. Actually, it's minus 4t, isn't it? And we add on the vector minus 2 and 0. Now, what you have to do at this stage is to equate like parts. So, first of all, we multiply everything out. And what we get is A equals 2AT plus B plus CT plus D plus T minus 2. So 2 times all of this plus 1 times all of this plus the T minus the 2. And then for the second row of the matrix, we've got C equals, well, this time it's 3 times AT plus B. So we've got 3AT plus, that's 2 there. So we've got a 3B there, plus 4, let me see, 3 times all of that, and then 4 times all of that, so it's plus 4CT plus 4D minus 4T plus 0, but we don't need the 0. We'll just leave this off there for now. So we've got 2AT plus 2B plus CT plus D plus T minus 2 in the first row, and then we've got C equals 3AT plus 3B plus 4CT plus 4D minus 4T plus 0. But we don't write the 0 in. Now what we do is, I'm going to show you how to do this, but I won't actually probably work out, solve the simultaneous equations, but basically we equate like parts, as it were. So we've got a 2AT here, and we've got a CT, and we've got a T. But nowhere else is there anything in terms of T. So if we just write that down, we've got 2AT plus CT plus T. And what is that equal to? Well, there's nothing else in terms of T, so it's just 0. There isn't a T at this side or another T at this side. So we just leave it like that. And underneath, well, let's just ring that. These are all the T's again. Excuse me. So we've got 3AT plus 4CT minus 4T, and that is also equal to 0 because there are no other T's around here, or anything like that, or any constants in terms of T. This system is equivalent. You can divide both sides by T in each equation to get 2A plus C plus 1 equals 0, and 3A plus 4C minus 4 equals 0. Now, before I write this system down again and tidy it up, I'm going to show you the fact that there is yet another pair of simultaneous equations. So here we've got a 2b, that's just a constant. We've got another constant, d there, and we've got a minus 2. And over here, these three constants equate with a. So we've got, so I'm going to write it down like this, 2b plus d minus 2 equals a. And then underneath we've got c, 3b and 4d. So we've got, and we'll put the c over here, and we've got 3b plus 4d and that's it. So we've got two sets of simultaneous equations, and I'll write those down more fully. So we've got 2a plus c equals 1, and 3a plus 4c equals 4. Actually, that's a minus 1. So we call that equation 1, equation 2, and also we've got a minus 2b minus d equals minus 2, and then we've got c minus 3b minus 4d equals 0, and that's equation 3, and that is equation 4. Now what you do is you solve 1 and 2 first, and you should presumably be able to do that. So if you solve 1 and 2 first, you find that let me just scroll up. So you find that A and C are, I'll write this in red. You want it to be highlighted. So A equals and C equals. So A equals minus 8 over 5, and C is equal to 11 over 5. Now what we do is we substitute A equals minus 8 over 5 into that, and C equals 11 over 5 into that. So what do we get? Well, we get minus 8 over 5, and I've forgotten the equation, so it's plus, no, it's minus 2b, isn't it? Let's just delete that. Scroll up a bit. So we've got minus 8 over 5, minus 2b minus d equals minus 2. And then we've got 11 over 5 minus 3b minus 4d equals 0. So we'll just call these we'll call that equation 5 and that equation 6. Equations 5 and 6 simplify to 2b minus d equals, what have I got here? Let me have a look. Well, with 2b, I better do it properly. So 2b minus d is equal to 2 minus 8 over 5. So what's 2 minus 8 over 5? Well, that becomes 10 over 5 minus 8 over 5. So that's 2/5. Right, so let's just scroll up a bit. So we just delete that. So that's equal to 2/5. We'll call that, just delete, oops, excuse me, just delete all that so that we're not crowded and so that everything's clear. So that's equation 7. And then the next equation simply can be written as 3b plus 4d equals 11/5. And that is equation 8. And you find if you solve equations 7 and 8, let me just, so solving 7 and 8, we get, or we find, that b equals -3/25, and d equals 16/25. Thus, we can write down, so if we just go back to, I think it was equation, was it what? It was equation 3. So if we go back to our complementary function, which is this, and add on this matrix 4 with all the values of A, B, C, and D replaced, then we will have our solution. So what we have is x and y equal to A times -1, 1, e to the power t, plus b, 1 and 3, times e to the 5t, plus, well, we've got -8/5t here. That -8/5 was the a, which we found, minus the b value, 3/25. Then if a was -8/5 and b was -3/25, then c is 11/25. Make that it's a little bit cramped, but anyway. And then here we've got for C, A, B, sorry, for D, we've got 16/25. And I actually like to write something like that with the fractions in it, like this: x, y equals A -1, 1 e to the t, plus B 1, 3, and I'm going to take a 1/25 out. So we've got plus 1/25 times the matrix, -40t -3, and that's 11t. Sorry, that should be a t there as well, shouldn't it? Yeah. And then that's just 16. In fact, actually, it shall be a plus 16. And in fact, this could have been written as let's just write that as a moment. There we are. I forgot the plus there as well. This could have been written as, take the t's out, put the t there, plus 1 over 25 times minus 3 and 16. That's just my fancy way of doing it. And that basically is the solution. Just a final note, you can actually, I've actually run out of space now, and without adding more pages, which is a bit difficult at this stage, because I've lost my cursor, I just want to write down here that you can write this equation so as x equals minus a e to the t, and that actually should be an e to the 5t there. I do miss things out, make errors. So plus b e to the 5t. And then, of course, you're better leaving that as minus 8 over 5t minus 3 over 25. And so separately, the y function is a e to the t plus 3b e to the 5t plus 11 over 25. Oops, coming off the page there. Let's just go down. Try and squeeze this on. So 11 over 25 t plus 16 over 25. And there we are. So those are the two solutions for the equation. Let me see where we are for equation 3. So we were given that, and we've solved it and obtained this set of matrix solutions and or the separate solutions written in this form. So I hope that's been helpful, and please look out for more of my videos, but I'll bid you farewell for now, and so I'll hopefully see you next time. So cheers for now, bye.